Good morning all. So we will discuss today the unit step response of second order systems. So as you know already in the previous session we discussed the unit step response of a first order system. Okay, so how we got the transfer function, then we have substituted for R of S input, and then we have modified that R of for applying the inverse Laplace transform, and applying the inverse Laplace transform you will get a time response. Okay, that is called as the final one. Okay, the same way we need to do it for second order system. Okay, so when the order is going to increase, so the difficulty in doing the analysis will increase. Okay, so second order, third order, because the denominator degree will increase. Okay, as the degrees increase, so its poles and roots will increase. Okay, because of that analysis will go complex. Okay, so but we will be restricting our analysis up to second order systems here. So maybe in advanced courses and all you will be going across second order systems. Okay, okay. So response of second order systems mainly depends on the damping ratio zeta. Okay, so you know the transfer function of second order system now, that is omega n square by s square plus 2 zeta omega ns plus omega n square. Okay, so that's the transfer function, and the main parameters are this damping ratio zeta and natural frequency omega n and the damping frequency omega d. So these are the three parameters we have discussed. Okay, so now to do the response. Okay, same way unit step response of second order system. So its analysis based on 4 different cases of the zeta values. Okay, so zeta equal to 0 means we have told undamped system. That means we are not applying any damping. So zeta greater than 0 less than 1 means there is a under damped system. You are slowly applying the damping. So that is the very important case we need to consider. Then zeta equal to 1 is critically damped system we call, and zeta greater than 1 is over damped. Okay, so it is not allowable. It becomes the system becomes stable. Okay, so damping and its types of damping also we have told. So just here I have stopped here. So let me consider that. Before that, a note I told we should not consider negative damping ratio. Okay, because it drive the system to unstableness. Okay, so the different types of system based on damping, as I told you, the how you apply the zeta value. Okay, over damped system means the transients in the system exponentially decrease to steady state without any oscillations. I will try to show you in next slide. Okay, how it will looks like. It does not have any oscillation at all. Directly it will go to the steady state. Okay, without any oscillations. And this is the case when zeta value is greater than 1. Okay, so there I have shown you mathematically. Now I am giving the definition of that. Okay, second one is the critically damped systems. Okay, so transients in the system decay to steady state without any oscillations in shortest possible time. Okay, so transients in the system decay to steady state without any oscillations in shortest possible time. Okay, so the zeta is equal to 1, that category. Okay, so both are looks like same. Okay, so little bit difference in the timing. Okay, so these two you will clearly you can see. Under damped systems means system transients oscillate with the amplitude of oscillation. Initially they will oscillate, and then gradually its amplitude decreases and finally comes to the steady state. Okay, that is 0. And undamped system means you are not applying damping. No, so system keeps on oscillating at its natural frequency without any decay in amplitude. It's like a just sine wave. Okay, so both positive and negative cycles with equal amplitude it will come. That is undamped. And when you start applying damping, so it will the oscillations begin to gradually decrease. And critically damped means it will try to without any oscillations it will come to the steady state. And over damped means a little bit faster it will reach the steady state. Okay, so that I will show you with a diagram here, so that will give you the idea what this about. See here, so undamped system means it is an oscillation. So see here, this is the wave. Okay, so you have, So this is what? Undamped system. Okay. So this waveform. So then you have the underdamped system. So underdamped system you see here. So this is amplitude is increased now. So then it is slowly, gradually decreasing, decreasing, finally coming to the steady state. Okay, we call that as 1. Okay, the steady state value as 1. So it is reaching that value. Okay, then critically damped means, so it will not get oscillation. See here. So this is the waveform here. It looks like, let me change the color. So this is the waveform. Okay, so directly coming to the steady state very fast, right? It is coming to the steady state very fast. It is called as critically damped system. Okay, and then over damped system. So see here, it will take a little bit later. It will not take a oscillation at all. It will come to the steady state. Okay, so that is over damped system. Okay, so this is about the idea and the different classification. So now we'll begin actually with the step response, and this derivation they will ask in the exam. Okay, very important derivation, and we are going to use this equation even in solving the problems also. Okay, next coming set of problem, first set of problems, it is based on this step response equation. Okay, so how we do it? So we know already the transfer function of second order system, which is omega n square by s square plus 2 zeta omega ns plus omega n square. Okay, in the previous session we have seen that. Okay, to show you once again, let me go back and we'll show you that here. So this is the transfer function of a second order system, omega n square by s square plus 2 zeta omega ns plus omega n square. What I need to find is y of t, time response, that is inverse Laplace transform of y of s. For that, what I have to do, this r of s, I have to take it in the numerator, and then I have to substitute for r of s as step response Laplace transform. Okay, that is 1 by s. Okay, so when you substitute that, you have to do this simplification to bring it into a form so that you can apply the inverse Laplace transform. Okay, so that only it is having the derivation. Okay, steps. So that we try to do. Okay, so r of s is equal to 1 by s, and this is the y of s. Okay, substituted here, omega n square by s, s square plus 2 zeta omega ns plus omega n square. Okay, so next what we'll do, so we'll consider the different cases now. Okay, so zeta equal to 0, zeta equal to 0, greater than 0, less than 1. Okay, so in that only zeta greater than 0, less than 1 is the very important derivation. Remaining all, just I am showing you how I am going to get that waveforms. Okay, just now I shown you, right? So like this, you will get 4 different waveforms for 4 different types of system. How exactly it is looks like its response. Okay, that I try to show you. So this is the case one where you have not applied any damping. That means 0 and zeta value is equal to 0. Okay, called as undamped system. So if you apply that, so what is your equation becomes? So here equation 2 zeta omega ns was there in denominator. So that zeta value substituted, that part will go off. So what is remaining is s into s square plus omega n square. So this you can easily, by partial fraction method, you can get the value of a and b. Okay, so that will come as 1 by s minus s by s square plus omega n square. Okay, so this is the form you'll get. I'm not going in detail with. Okay, so just to show you the response. Now if I apply the inverse Laplace transform of that, so it is going to be, so 1 by s is 1, and s by s square plus omega n square, from the inverse Laplace transform table, you know, it is cos theta. Okay, but in the theta place we have omega n. That's why omega n t. So 1 minus cos omega n t. So that's why. So you will have the cos signs here. Okay, that is coming starting from here. Okay, so when amplitude is 1, so what will happen here? 1 is there. 1 minus 1, it becomes 0. That's why it will start from this place. Okay, and then it will start oscillating as cosine wave. Okay. So this is about the waveform for undamped system when zeta equal to 0. So this is the very straight away, because zeta value removed, no? So it becomes a normal equation and you will get the a and b values. Apply the inverse Laplace transform, you will get the response. So now we'll go to second case, which is the important one. So zeta value greater than 0, less than 1. Okay. So you should be cautiously look at these steps. Okay. So omega n square again substituted here. So this is the equation now. Now zeta value is not 0. Earlier it was 0. That's why I removed it. That's why s square plus omega n square came. Now zeta value is increasing, greater than 0, less than 1. That's why it should be there in the equation. So now you have to consider again partial fraction method, and you have to simplify that. For this 1 by s part, you can write it as a by s. Okay. Whereas the second part, what you have in denominator, you have a quadratic equation. For quadratic equation, you know how it will come in the numerator. It will be coming as actually bx plus c. In the place of x, we have now s. Okay. That's why s is written there, bs plus c divided by this one. So if you split this, you will get a form so that you can apply easily the inverse Laplace transform. For that only we are doing. So to get the values of ABC now, I have done this. Okay. So left side we will be writing whatever we have here, omega n square s into s square plus 2. So this, you know, this is mathematics. Okay. Not any control system technique. So it is mathematics equal to. So then you are taking the LCM here. So a equal to a into s square plus 2 zeta omega n s plus omega n square. And here bs plus c into s will come. So as it is numerator, so these both denominator part will cancel out in the both side. Okay. So this side. So only the numerator part is remaining. So that we write omega n square equal to, and we'll group the s square, s and constant terms. So s square term, what you have here, b s into s is there, bs square, and here a into s square is there. So if you are not following, you can write one more step, multiplication. Okay. So I have written directly so that a plus b s square will come as s square coefficients. Then 2 zeta omega n s into a. Okay. Here one s term is there, and here c into s is there. So that's why s term coefficients, you'll get 2a zeta omega n plus c. Anyhow, you can write 2, you have to write normally first. Okay. The numbers now. You have to write like that. Okay. Plus constant. What is constant here? A into omega n square. Okay. So that is the constant. So now we have to compare the coefficients with left side. So left side, you don't have any s square or s terms, right? Only you have the constant. Only that constant we will equate it. So equating the coefficients, what you will get, omega n square at the left side, and right side constant is a omega n square. So from this, what you will get, a value, it is both are cancelled, a equal to 1. Okay. So then we'll go to s square term. So s square term is anyhow it is 0, right? So a plus b we can 0 we can make, and we can get the second value b, which is minus a. Minus a means a value is 1. So whichever is easiest one, we'll take that first and we'll get the value 1. Okay. Then from that only 2 coefficients are there. We can take the next set of value. So now since a and b values is known, so c value is very easy to find out. So equate the coefficients of s. Okay. So what you have, 2 zeta omega n into a plus c equal to 0. So c is nothing but 1 minus of 2a zeta omega n. So a is 1. That's why minus 2 zeta omega n is the value of c. So now this a, b, c value you have to substitute back in this equation. What is that? A value 1 by s plus b is just s, and c is minus, right? S minus 2 zeta omega n. Like that you have to substitute, and we have to do the further simplification. Okay. So I hope you are able to understand this. Okay. So just you have to write down once you get the notes. Okay. So y of s. Okay. So left side it is no change as it is. I'm writing. Right side I am substituted the ABC values. So it looks like, and here minus sign is taken outside. That's why it came plus here. Okay. So plus into what you had, b value is minus 1, right? B value is minus 1, c value is minus 2 zeta omega n. Both minus we have taken outside. That's why it got plus here. Hope it is clear. So now we'll continue. So what I will do is in the numerator, I have a 2 zeta omega n factor. I can split this into 2 zeta omega n plus zeta omega n. A plus a is 2a, right? Same way. So I will split that. See here. So first part no changes. Second part here, s plus zeta omega n plus zeta omega n. Okay, I will write like that. Denominator no changes, little changes, right? Okay, denominator what I have done, I want to bring it in a complete square. So for that, what is there here? S square is there. Okay, and for s is there here, and 2 is there. So you know a plus b whole square formula, a square plus 2ab plus b square, right? So now here s square is there, a part is there, and 2a is there. B part is this one. So you'll identify now B part zeta omega n. So you need to get the square of these terms. Okay. So that is zeta square omega n square. You have to add and subtract so that equation may not alter. Okay, the actual equation should not alter. So this is the B part you have identified from this. So that you have to add it and subtract it. Okay, from this equation, and you have to continue the discussion. Okay, so I have not shown that, maybe directly I have written the simplification. Okay, so for this equation I will add zeta square omega n square minus zeta square. So it will both cancel out, right? It is not going to do anything, but we will not cancel it. We'll group in such a manner that we'll get a plus b whole square. So that's why here numerator I have grouped here s plus zeta omega n, and 1 plus zeta omega n I have kept outside. Okay, no changes to numerator value also. In the denominator, so now what will become? So when I add zeta square omega n square, I can write a plus b whole square. A value is s, b value is zeta omega n. So it is s plus zeta omega n square. Okay, and then plus omega n square is already there, and this minus zeta omega n square comes from this addition. Okay, so this is outside. So now even if you split this, s square plus zeta square omega n square plus 2 zeta omega n s, if you write like that, so then this equation only will get. Okay, so just to get a simplification, okay, in the inverse Laplace transform, we need to do these modifications. Okay, I hope you understood how the numerator 2 zeta omega n is splitted. Denominator, I try to get a plus b square form. For that I have identified the b part, and that b part I have squared it and subtracted it so that equation is not altered. So then I have grouped the a plus b square and these terms. So next, so 1 by s as it is minus numerator I have separated this. Okay, so here let it be like this. Next step I have grouped it. Okay, and in the denominator what I will do, so 1 s plus zeta omega n, so square I have removed here. Okay, so maybe some typing mistake while writing. Okay, so you add that in notes. Okay, plus here omega n square I will take common. So what will happen? Omega n square 1 minus zeta square. Okay, so what is this value? So you know last time I told you the three values, omega n, omega d, zeta. So what is this omega d value you have seen there? So if you have written down the notes, okay, I hope I have not given, right? So omega n square root of 1 minus zeta square is the relation between omega n, that is the natural frequency, and the damped frequency. So this is the relation between omega n and omega d. So now what I have here is omega n square is there, and this square root is removed. 1 minus zeta square is there. Nothing but what? So it is omega d square. So this term, so this complete term is a omega d square. So that's what I have done in the substitution here. See here, omega d square, omega d square. So I have splitted here equation, that also I will show you. So in the next step, what I have done, so this plus is there, no, this part I have separated out. Okay, so what I have made is the denominator I have kept both same. So this is the first term. Okay, so this is the first term, and the second term is this. Okay, and when you are separating out, so you have to be cautious about the sign also. Okay, like that I have separated out. So what is the first separation? So it is minus sign is there. Minus sign will multiply s plus zeta omega n divided by whole denominator, s plus zeta omega n whole square, plus this one I have substituted as omega d. So as I told you, so omega d square. Okay, so again writing steps now it will increase. That's why grouped it. Okay, two steps in a one I have grouped it. Okay. So hope you understand. Then here plus sign is there, but outside minus sign is there. That's why it will minus, it will come when you separate out. Okay, so that's why this minus will come. Then zeta omega n is in the numerator. Denominator same term, s plus zeta omega n square plus omega d square. Okay, so till here hope you understood. So we have substituted the R of s value here 1 by s, then separated out.
Sir, I didn't
by
understand the third step.
this one.
So that s plus zeta omega n whole square plus omega n whole square.
Okay, when you are writing that, I will hope you understand. Let me, I will repeat. Okay, so here first ABC values I have substituted and minus sign I have taken outside. You got this. Then I have 2 zeta omega n I have separated here. So it is zeta omega n, zeta omega n. Okay, and here to bring it in a plus b whole square form, what I have done, this is a I have identified. A square is there already. And second part is 2s is there. So 2a is there. B term is not there. So B term I have identified now, zeta omega n. So that I have added and subtracted to this denominator equation. So then next step what I have done, so I have written this, when I have added zeta square omega n square, I can write now s plus zeta omega n whole square. Okay, so in that only this will group out. Then whatever remaining we'll write down. So omega n square already was there, it is written, and minus zeta square omega n square we have added no for equating, so that will come over. So then, so omega n square is here common, so 1 minus zeta square will come in the denominator, and here s plus zeta omega n I will group, and zeta omega n I will keep it separate. Okay, so next step what I will do, this one I will substitute omega d square. Okay, so this is omega d. Omega d is given as omega n into square root of 1 minus zeta square. Okay, I will send you the note, so you'll know the relation. I told you derivation is not important. So that is the relation between damped and natural frequency. So this is there, omega d square. Now I will separate out normal, no? So you are when you have two terms with LCM is common, you can combine it. Same way, I'm going to separate it out for my advantage. Okay, to apply the inverse Laplace transform. So I will keep the numerator this one, and the denominator, whole denominator is same. Then this I will separate it out. This is the third step, right? So now minus sign is also there outside, that also you should be cautious. So minus s plus zeta omega n divided by whole denominator. So s plus zeta omega n whole square, it is there already. So here missed, I told you, write down that. And this one I have substituted omega d square. That's why it looks like this short. Then here plus sign is there. Okay, so that's why I have put the bracket here. Okay, even you can split here also, but I want to group these two together. Okay, so that I can get some form. I will tell you later how it will come. So this only I have split and minus 2 zeta omega n by again the same denominator, s plus zeta omega n square plus omega d square. Okay, so we'll continue. So the same thing. So next step what I will do. So y of s equal to 1 by s, this is no changes. Okay, s plus zeta omega n by s plus zeta omega n square plus omega d square. So here also no changes. In the third part what I will do, so you know the sine omega t and cos omega t relation in Laplace transform. It is one will come, sine will come as a divided by s square plus a square. Laplace transform of sine omega t is a divided by s square plus omega square, right? I hope this you know. So this is the relation, Laplace transform. And for cos theta, what is the thing? Cos a theta, it is omega by s square plus omega square. Okay, I want to get this form because I told you no, there is oscillation is there in the 0 to 1 case. Okay, that's why I have to bring in sine and cos form. That's why I have done that modifications. So for that, so if I have written zeta omega n, I have not satisfied this part. Okay, so what is the satisfying factor here? So whatever is there in numerator w, it should be there here, it's a square. Only then I can apply the inverse Laplace transform and I can get cos, right? Similarly here, if here what will be there? Here also same. Okay, so here s will be, sorry, I reverse, I told you. For sine it is constant should be there, a. Okay, here it is w, and for cosine it will be s should be there, right? So to bring it in form, what I will do, so just I will numerator and denominator I will keep the omega d. Because of that, no equation will change. No, previous this equation was there, third part, zeta omega n by s square plus zeta omega n whole square plus omega d square. Now I have added just omega d and omega d in the denominator. So because of that, so I can apply the inverse Laplace transform for this part easily, and I can keep this as a constant. So this will come as sine omega dt. Okay, sine at. So in that place you will
So
get
randomly we are subtracting this part.
random subtraction means what?
So that zeta
See,
omega n
this is,
divided by omega d.
your voice is not audible.
So that zeta omega n divided by omega d, that full part.
Yeah, this is why we will do. We will be doing this. This is not a control system part. I'm telling you, this is Laplace transform. Last time you have did it. Various sine triangular way when we have did it, and we try to apply the inverse Laplace transform. What we have did, we have to bring it in a form so that we can apply the inverse Laplace transform. I can directly show you this step. See here. I'm applying here inverse Laplace transform here. To bring it that form, I'm explaining all these things. Okay, how you got these steps. Okay, so what you do is after going this, so you go through the notes. Okay, so you'll understand, but definitely you'll understand. You have to do day by day work. So what I have done here, so previous slide I will show you. Okay, see here. This year till here I hope you have understood. Okay, if you are coming late to class, then I am not responsible. Okay, so see here. So till here I got this third part. What I am doing here now, I have want omega d in the numerator. Okay, if I have omega d, then I can take zeta omega n as constant and I can separate out. Okay, just a minute. Okay, omega d, if it is there in numerator, zeta omega n constant I can separate out, and this part I can write sine omega dt. Okay, so you should know the formula, everything. Okay, so you can refer after the class. So that only I'm doing it here. There is no much big things I'm doing. Okay, both will subtract if you want to get the previous equation. Okay, but I want to bring here omega d, means I want to put omega d in the denominator also. Okay, so equation should not be modified. So that's what I have done. So now this part as a form cos, and this form is in the form sine. Okay, and again what I will do here, omega n is there and omega d I will substitute here. What is omega d value? Again omega n into square root of 1 minus. So if you are writing, you can write each step. Okay, if you require. I sometimes clubbed 2 steps because to reduce the time. Okay, so now when I write this omega d, this if I substitute here, this denominator omega n, numerator omega n cancel out, and what is remaining is zeta by square root of 1 minus zeta square. So this is the derivation. So now I will apply the inverse Laplace transform for this y of s. Okay, so what you will get, 1 by s is one factor, and then this is s divided by, okay, s plus a divided by s plus a whole square plus b square. So this also, you know, hyperbolic function like that. Okay, so this complete s term now. So same thing, it should be there for applying cos, and here omega d is the constant. Similarly here omega d is, it is in sine form now, omega d by s plus omega n square plus omega d square, and here I have told you this I have substituted. Okay, and this omega n cancel out, zeta by square root of 1 minus zeta square is remaining. I would have shown this step and I have written this, but again you have to write that equation in exam. For that I have clubbed here many steps. Okay, so now inverse Laplace transform will apply. 1 by s inverse Laplace transform is 1, you know, and this is here. So here factor is zeta omega n, that's why e to the power minus 80. E to the power minus 80, what you will get? E to the power minus zeta omega n into t you will get. Okay, into, it is a cos factor, right? So cos factor e to the power 80 is clubbed. So this table I have given you in the network theory in Laplace transform. Okay, e to the power minus 80 into cos is there, what will be the Laplace transform, like that I have given. Or else you can refer any internet also, Google it, you will get the equation. Okay, so this e to the power a place, you got zeta omega n, and then b place you have omega d, so that's why cos b theta, cos omega d t. Okay, this is the second part, inverse Laplace transform. Third thing, you have the constant here, zeta by square root of 1 minus zeta square here as it is. Again here a term is zeta omega n is there, that's why e to the power minus zeta omega n into t. Then it is omega d sine, now it is sine omega dt. Okay, so this is the equation you got. So till here if you have understood, so you are in a little better stage. So next step what I will do, I have here something common, right? E to the power minus zeta omega n t, in both equations I have common, right? So I can bring it. Okay, so that I will do in next step. See here. So the last step we have come across. So I have grouped this, e to the power minus zeta omega n t is common, and I have taken square root of 1 minus zeta square outside. Okay, so I am grouping now again. Okay, both the terms. That's why minus sign you should be cautious. Minus is outside I have kept. So here the cos term, you didn't have this term, right? If you want to get this outside, okay, let me show you that. You can roughly, you can work that also. Okay, if you are not following, it is better one. So what I'm going to do here, this is a different term. and this is a different term. I want to club this both. Okay, minus sign is there both common. That's why minus I will take outside, and e to the power minus zeta omega nt is there common. I will take that outside. Okay, and again one more step I can write next. So that two step again I have combined here. So what I have done is I want square root of 1 minus zeta square. This I have taken outside. Okay, together saying, so this complete I have taken common. E to the power minus zeta omega nt by square root of 1 minus zeta square I have taken outside. When I take that outside, so to satisfy the equation, what I should do, this cos omega dt, I want to multiply this term, right? Only then you will get cos omega dt. Okay, and here no need to write, already it is there in the denominator. So that's why just zeta into sine omega dt which will come. Okay, so that only I have done. So these things when you write down only you will understand. Okay, so because of this situation we will be not writing, but you can do parallelly there roughly. Okay, so this is 1 e to the power minus zeta omega nt by square root of 1 minus zeta, and whatever I'm explaining, it is completely mathematics. Okay, so it is not the control system aspect. Okay, I want to get the inverse Laplace transform so that I should find the time response. Okay, so that's what cos omega t, there was this factor was not there. That's why you need to multiply. So when you multiply this with outside term, it will cancel out, right? So satisfying the equation. Why I'm doing this, I will tell you. Okay, omega d t plus zeta into sine omega dt you will get when you take these two things common. Taking common things and all, it is not a new thing. Okay, very simple. So now what I will consider here is I want to bring it. So now what I will do. So this something is that two factors are there, square root of 1 minus zeta square cos omega dt and zeta into sine omega dt. So what I will try to do here is zeta part, I will try to substitute some sine or cos, so that I can get sine a cos b cos a sine b some form. Okay, so that I can still simplify this form. Okay, so for that what I will do, I will consider 1 minus square root of 1 minus zeta square, whatever is there, I will consider it as sine theta. Okay, if you consider this whole term as sine theta, what will be the zeta value here? So take square on both sides. Okay, so then 1 minus zeta square equal to sine square theta. Zeta square is equal to 1 minus sine square theta. Zeta equal to square root of 1 minus sine square theta. This trigonometric relation. So from that, you know, it is cos theta. Or else if you substitute zeta equal to cos theta, so what is square root of 1 minus cos square theta? Sin theta, right? So this only I will try to substitute in the place of this square root of 1 minus zeta square and zeta. Okay, so when you substitute that, what will happen? Even you can take the ratio of this. Tan theta is nothing but sin theta by cos theta, which is this factor, it will come. So if you take the inverse of tan, that will be the theta. Theta is one of the important aspect in the oscillations, right? Phase. Okay, so even you can consider this as theta value. Okay, we'll be using this in formula problems and all. That's why I written that. So that if I do, so what will be my formula now? It looks like this: y of t equal to 1 minus, this is as it is outside. So here I have substituted sin theta into cos omega dt and then cos theta into sin omega dt. So now you have to use. So how I have applied, I will show you in next steps. Okay, sin a cos b cos a sin b formula. Okay, so using, so reverse way I have written. Okay, sin a cos b cos a sin b. So this is the formula. But what I have done there, which one I have taken b, which one I have taken a, to show like this, I have written that. Okay, so just let me go back. So this is b I have taken. I have taken b and this is taken a. That's why sin b cos a, then cos a sin b. So formula is what? Sin a plus b, the trigonometric relation. Okay, so that only I have used here. So sin AB or sin B plus A, there is no difference, right? So that's why B only written first here, right? So 1 minus e to the power minus zeta omega nt square root of 1 minus zeta square sin omega d into t plus theta. Okay, so this is the final derivation. Okay, this is very important derivation and important relation for problems also. Okay, you need to remember now. Okay, so first thing you have to remember the standard transfer function of the second order system, omega n square by omega n square divided by, what is that, s square plus 2 zeta omega ns plus omega n square. Okay, and this relation now. Next, okay, y of t is equal to 1 minus, I can remember this anytime, e to the power minus zeta omega nt divided by square root of 1 minus zeta square sine omega dt plus theta, because I have written many times, okay, and explained many times, okay. So you will get that. So don't worry, since it is first time, maybe here and there some steps are missing. So you go work on that. Okay, I will send the notes after this session. Okay. So what is theta from this? It is either cos inverse zeta or it is sine inverse square root of 1 minus zeta square. So you can use many relation here for theta. One is cos inverse zeta, another is sine inverse square root of 1 minus zeta square, or else tan theta form also you can use, square root of 1 minus zeta square by zeta. That previous one I have shown, no? So three values are there for theta. So if you want to find theta value, you can use either of this relation. And if the same waveform, if you draw it in a graphical way, it looks like this. See here. So this is your underdamped system. So initially it will increase, then slowly decrease. It will come to the steady state. And this, why it is oscillation? Because of this sine omega dt. Sine is there, no term. Because of this oscillation, since e to the power minus 8 is there, exponential, because of that this decaying will happen. Okay, so both it is combined here, multiplied here. Because of that you will get the underdamped response. So if you consider zeta value 0 here, what will happen? This denominator becomes 1. Here this part will go away. E to the power 0 is 1. Only 1 minus sine it will come, right? So then just you will see the oscillation. If you have a simulator now, computer simulator, if this equation is put and if you are putting the zeta value, you can clearly see this. Okay, so when before applying zeta value, this was just like a oscillation, and as we apply the zeta, slowly increase it from 0 to 1, so it will take this form. Initially it was having the increase. As zeta is increased, its amplitude try to decrease, and when it reaches some zeta value, okay, some percentage of zeta value, it will come to the steady state. That's why it's zeta. So your problem, when you solve that, you will come to know what is the zeta value. Probably it will come in the calculation. Okay, so this is about the response under damped system. Second case, this is the very important case. Okay, so now we will go to the remaining two cases. Just I will briefly show you. Don't go in detail because you will not understand. This only you felt difficult, that you don't understand. Just I will show you the response and the this one, okay, graph. So zeta equal to 1, next case, critically damped system. So again, what you have to do, zeta equal to 1, you have to substitute. When you substitute zeta equal to 1 here, what will happen here? See, so zeta equal to 2 zeta omega ns is the standard form. So zeta is 1, 2 omega ns. So now this s is a and omega n is b. It is 2ab. So it is directly s plus omega n whole square now. Okay, and it is s. So you can easily apply the partial fraction method and you can find out the ab value, inverse Laplace transform, you'll get the response. So steps is there, I have not shown because directly I will show you the response, because that is not asked in exam. Okay, so just you should know, and if it is asked also, you should able to do that. It is very simple mathematics, right? So 1 by s minus, so this is the ABC value, you'll get AB 1 by s minus 1 by s plus omega n minus omega n by s plus omega n square form will get. Apply the inverse Laplace transform. 1 by s means 1 by s plus omega n, 1 by s plus a, it is e to the power minus 80, e to the power minus omega n into t. Then this is omega n into t, e to the power minus zeta omega n t. Okay, so this is the response. Okay, so if you same response, if you're, so see in this equation, anywhere you see any sign form? No, only e to the power minus zeta is there, decaying term is there. That's why you will have the two decaying terms are there. That's why it will very fast, it will come to the steady state. Okay, so this is what about the response of the zeta equal to 1 or critically damped system case. And finally we have zeta greater than 1 over damped system. So that case also you need to consider again the zeta value. Okay, so in this case, in different manner it is splitted. Previously I have done for getting that form. Okay, what I have done, so ABC values I have find out and I have written. So here some other form they have written. Okay, the same equation modified like this. Any number of rearrangements you can do. Such rearrangements, they got this value. Okay, again in this value you are getting only eta e to the power terms. There is no sine terms. That only you can observe here, and that's why because of that it will reach the steady state, only reach the steady state. It may be delayed, but it will try to go directly to steady state. Okay, little bit later. So this is about the 4 response what you have. Okay, so in that only second one was the important one. So I will quickly recall. Okay. Okay. Very first. Okay, this is the second order system I told you, and this is the block diagram of a standard block diagram of a second order system. From that you got this transfer function. Okay, s square plus 2 zeta omega ns plus omega n square. So you need to apply the input R of s as unit step, because the response is unit step. Same way you can find unit ramp, unit parabolic. Imagine now for step a simple input only you got such a difficulty. If you apply parabolic ramp, how difficult it is. Okay, manually it is very difficult to do the analysis also. So that's why nowadays computers are used. Okay, tools are there, MATLAB simulators are there. They will be used for doing these analysis and all. Okay, but for doing manual analysis you should know, no, as a very first student of control system, that's why only they have kept second order system, that you try to understand. That's why they have kept that. Okay, and for that there are parameters we have understood. Omega n, system natural frequency. Zeta is damping ratio. Okay, this definition I have given, and this relation I have given, see here. Okay, omega d is equal to omega n square root of 1 minus zeta square. This is the relation we'll be using. Okay, so 2 times I have used that, right? So that is from this. Then the 4 different systems I have defined in mathematical as well as definition. So zeta equal to 0 means undamped. You are not applying any damping, so it will oscillate, just sinusoidal wave. When you apply zeta value, try to increase it. Okay, 0 to 0 0.1, 0 0.2, 0 0.3, 0 0.5 till up to 1. So that stage is called as underdamped system. So your oscillation is there in the beginning. Later on, the amplitude will decrease, and it will come to the steady state. So this is very interesting case. Okay, and in this only we will be work on. Okay, then zeta equal to 1. When it reaches the zeta value, you are keep on increasing, like in a tabular column, 0.2, 0.6, 0.8, finally it reaches 1, right? When it reaches 1, that system we call it as critically damped system. You will see no more oscillations. You will see only reaching the steady state. And again, zeta greater than 1, if you increase 1.2, 1.5, 2, 3, 5, 10, 100 like that, so you'll see only decaying. Okay, there is no oscillation at all. Okay, that's what I tried to show you. So this is the definition wise I have told you. Okay, what is there in this? So this is the graph I have shown you. Okay, so in the undamped system you'll have the oscillations. In underdamped system, initially you will have oscillation and finally it will come to steady state. Critically damped system, you don't have any sinusoidal wave, directly it is exponential term, it is reaching to steady state. And then this is overdamped system. So then we try to take one by one step. R of s is 1 by s. So this is the y of s now. Okay, y of s by r of s was the transfer function. R of s I have taken in numerator, and numerator R of s 1 by s substituted. That's why s came in the denominator. Now this is the form. Using this, we need to do the zeta value you have to apply here. 0, 0 to 1, 1 greater than 1, like that, and we have done the analysis. Okay, so zeta equal to 0 when you apply, so it will be, this term will vanish out, and what is there? S square plus omega n square. So accordingly you have to do the analysis. Then zeta greater than 0, less than 1, you need to consider this. For that I have done another type of analysis. When zeta value is equal to 1, it will come s plus omega n whole square. Okay, so that also we have seen. Then zeta greater than 1, it will be complex. Okay, so that's why it is in different manner done. So you no need to crack about that equation. Only you bother about the zeta value 0 to 1 and maybe 1 equal to 1, like that. Okay, even 0 also you'll understand. See here, 0, it is nothing is there. So s square plus omega n square will come. So you'll split it in partial fraction method. You will apply 1 minus cos omega n t. This waveform you will get. Okay. So then we have taken zeta greater than 0, less than 1 form. And these are the A, B, S, C. Okay. Because of quadratic equation, it will come. So first part you have done A, B, C values you have calculated. Then you have substituted that. And then you have modified the equation to bring it in a form. Okay. So these are the arrangements you have done. Finally, we applied a Laplace transform, inverse Laplace transform. You got this equation. Then this equation again you have simplified it. Okay. And finally you got a form. like this. Okay. And if you draw this waveform, see here, sine term is also there, is there, exponential term is also there. And both are multiplied. Because of that, initially it is having sinusoidal wave. And because of exponential, it is trying to decrease its amplitude value. So this is how the response. And this is very important one. Based on that only, we will define next the specifications. Okay, time response specifications we will define based on this response. Okay, then zeta greater equal to 1. I told you it is s plus omega n whole square will come. Again, inverse Laplace transform, AB value you have calculated, written that, and this response looks like this. What is observation is there is no sine term here, only e to the power minus, that is decaying terms of exponential you have. Then zeta greater than 1, again, this is the thing. Okay. So I hope you will not understand this zeta greater than 1. Don't worry. I have included that in, okay, to show you. Okay. This thing you have to practice, which is 1, zeta greater than 0, less than 1. This is very important. Work out 1 or 2 or 3 times, how many times till you understand. First time you see and write, second time you see and write, third time you, without seeing, you try to do the simplification, you will get it. Okay. So I will stop for here, and tomorrow we'll see the problems based on this time response of second order system.